Okay, so I guess we should be getting ready to go. Are you guys ready on that end, Berkeley?
94.
Cool. Why don't we get going? It's strange to introduce Armando without actually being able to see him physically. Armando's really good.
See me. Hold on.
Oh, okay.
Hold on.
Holding. Oh, whoa, there we go. Hey, Armando. Here I am. Hello. This internet thing, there's something in it. I'm really pleased to introduce Armando. He's a good friend of mine. We were office mates for about 3 years back at UC Berkeley when we were graduate students there. Armando's done a huge amount of work on topics ranging from mobile computing to reliable computing to ubiquitous computing. He's also had a long-standing interest in computing history, co-teaching a course with me and Randy Katz way back in 1998 to freshmen and doing a number of courses and seminars at Stanford. These days, Armando is a research associate at UC Berkeley in the RAD Lab. I think he's a co-founder of the RAD Lab, along with David Patterson. And if you wanted to know some random but interesting things about Armando, here's 3. First, he has won Ben Stein's money. Secondly, he's a classically trained pianist who has been the music director of a number of community theater performances.
Including
and thirdly, say that again?
Including one going on right now.
I'll
sell tickets after the lecture's over.
And the third thing that I'll say about Armando is if you ever want really good tasting wine in a box, talk to Armando and he'll let you know what to get. With that, Armando, why don't you take it away?
Thank you, Steve. It is equally a pleasure for me to be introduced by Steve, with whom I think some of the work that I'm really proudest of was done back when he and I were grad students here, so that was cool. And some of you may or may not know that part of that actually did involve teaching what was then a freshman seminar on the history of computing, and I can only assume that that's how Steve convinced Ed Lazowska to talk me into doing this. So I'm going to try to talk about the origins of software, and it seems like the kind of thing that somebody who's been doing computer science for a while should have a pretty good grip on. Is this generally an interactive thing, by the way? Is it reasonable to ask questions and expect people to respond in close to real time?
Yep, exactly right.
Okay, I'm going to attempt it.
Or we can do it.
I'm going to attempt to do some of it as I go to try to engage people in the topic a little bit. So before I start the actual content, I need to pre-apologize for a few things. I'm going to be talking about the origins of software, but as you can probably tell, I wasn't there for a lot of the dates of some of the events that I'm going to discuss. So it's all second source stuff. What I'm trying to do is put a perspective on it that pulls the different pieces together so you can see what I think is an important trend in how software came to sort of be the tail that wags the dog. This is not an exhaustive survey of computing history, obviously. That means that I'm going to probably end up leaving out a lot of people or artifacts that are really important, but I had to choose what I could include in just telling the story of software in about an hour and a half. Also, I have a particular point of view about how I think the evolution of software has happened and what has characterized it. And in order to present that perspective, I'm going to be using some terminology and some conceptual vocabulary that didn't really exist at the time that these events occurred. So the way that we see these events in retrospect, obviously, is not necessarily how they were seen at the time. And I guess the last disclaimer is your mileage may vary. Steve said that this Steve Maurer, said that he wanted someone who actually had a point of view and was willing to, sort of stand up and make some positive statements about it. I am that kind of person. My point of view is not the only way to look at software history, and I have a lot of suggestions at the end on resources where you can go to learn a whole lot more. So, having said that, what I'm going to try to do is present an outline of what I think the intellectual concepts have been behind the way that software has evolved. Some influential people and the artifacts with which those people are associated. This is, after all, an engineering discipline, so it's very rare to talk about an influential person without a corresponding artifact, and vice versa. And lastly, about what has sort of been the wider impact of the trends that I think I identify as being important ones for the evolution of software. Now, I don't know how this works in terms of if people want to ask a question from a remote classroom, is there some way that I'm notified of that? Is there like a blank light? What is?
We just yell.
We yell as loud as we can.
Okay, you may have to yell fairly loudly, since I tend to speak fairly loudly. But if I don't respond the first time, please continue to butt in, and I will eventually understand that something's happening. My brain cell will turn to that. It's been a long day. Okay, having said that, my first slide is deliberately left blank, because this is the point where you, the audience, get to contribute to me what you think software is. It occurred to me that in order to talk about the origins of it, we had to have some agreement on what it was we were going. Anybody want to take a shot in the dark? Bueller? Anyone locally? Come on, Cal folks. What's software?
Microcode.
Again?
CPU microcode.
Okay, we've started the ball rolling. CPU microcode. We will get less technical for those of you who are non-technical. Don't worry. Anybody else? A little more general software. What is it not?
It's not hardware.
It is not hardware. Good. I was looking for that. For the $250 question, if it's not hardware, why do you care about it? Instructions to operate. Thank you. That was said by someone in the room at Cal. Cal 1, everybody else 0. We're keeping score now, folks. So there's a lot of ways to look at what software is. And I think the reason that it's not obvious how to answer the question is that when computers started to be built and actually used for solving useful problems, it wasn't clear that there was a distinction between hardware and software the way that there is now. So the origins of that distinction are what we hope to get at. There's two different tacks that you could take in asking what software is. One is you could say, well, software is information. You can look in books and see listings of software code. You can talk about an algorithm producing a certain result or performing a certain function. Those are all abstract ideas. They're not tied to any physical representation. On the other hand, software can also be thought of as a machine because when you pair up the software with hardware, ideally, it actually does compute something or produce a useful result or play a song or draw a picture. So you can't tease the two pieces completely apart, and software ends up having sort of this, Zen-like duality, right? It's both an abstract, non-physical expression of information, but it also has a characteristic in which you can really view it as being a machine because it directs the operation of physical hardware. So we can compromise by saying that maybe it's a symbolic representation.
Question for Microsoft.
Question for Microsoft?
Yes.
You say that it must be performed by a physical device, but if we had some code that was going to go and be run on a quantum computer, which doesn't exist yet, does that count?
When it's invented, I'll tell you. No, I don't mean to be flip about that. The physical device part is open to broad interpretation. In fact, there used to be this joke about, how do you make a computer that has no hardware? And the stock answer is, well, you start with some hardware, and then you put software on top of it that emulates a computer. Then you put some other software on top of that that emulates a different computer. Then you run your program, and then you very carefully remove the hardware. It doesn't work in real life. But we're going to stick to the convention for the purposes of today's meeting that at some point you have to get a physical device to do something in order to compute a result, quantum notwithstanding. So if you're going to talk about a symbolic representation of doing some sort of a task, obviously you need a vocabulary to talk about how you would express that task. And to get an idea of where the origins of this stuff was, brief show of hands, or actually waving of hands, if you've seen a Jacquard loom or have heard reference to Jacquard loom, wave hands violently because otherwise it's hard to tell. It's also really fun to see people doing that. Okay, thank you. So for those of you who haven't seen it, or as a review for those of you who have, the Jacquard loom was quite the rage for textile weaving in the early 19th century, and I've tried to create this lovely PowerPoint schematic of the way it works. This is an actual photograph of a working replica of a Jacquard loom. I'm hesitant to draw on this, but I guess I believe it'll work. Yes, that's the actual photograph. And this is the kind of textile that you could produce, which at the time was far more precise for these geometric patterns than anything that a human could weave without assistance. And the way the machine works is that there's this spool that feeds punched cards through the shuttle. And the idea is that the cards have holes in certain places. I've drawn kind of a schematic looking edge on. So imagine that these black lines are sort of you're looking kind of at the edge of the card, and where you see the gaps is where the card has had holes punched out of it. So the idea is that as the cards are being fed through the machine, there's a set of hooks that basically drop down and try to catch these threads, which have been pre-staged. And if there's a hole in the card above the appropriate thread, then the hook will grab it. If there's no hole, then the hook will be prevented from dropping all the way down. The hooks that have dropped down then pull a few threads up with them. And although this is a little bit simplified, it captures the general idea of how the loom works. Right? So this is an early example of the concept of programming a loom to weave something. And I think that's a good example from which we can kind of pull out three aspects of software. One aspect is that there's logical structure, right? So there's a correspondence between the pattern of holes in the card and what the finished textile will look like. And if you understood how the machine was organized, and I showed you a card, you could probably work out what pattern that card is going to weave. There's an issue of representation, right? So the cards are physical artifacts that have holes in them, But the essence of what the card tells you is something that can be encoded as information independent of the card itself. Right? We could write down, for example, a sequence of ones and zeros on paper which represent where the holes would be. And then if the cards are lost, we just get out the piece of paper and we can repunch new cards from the information. Right? So this is the software's information aspect, that destroying the physical medium that carries the software doesn't destroy the information that the software was intended to encode. And lastly, there's the structure of the physical device and how the software is connected to that. So, obviously the positioning of the holes is related to the positioning of the weaving hooks. In other words, if the holes in the card are the wrong distance apart, and if they don't match the hooks on the machine, then the machine won't work. The speed at which you feed the cards through the machine has to be coupled to the speed at which the shuttle can move. So, in other words, the card is useless without knowing the machine geometry. Right? If you had a stack of cards, you would need more than just the pattern on the cards. You need to know how the machine was arranged that originally played the cards back. And if you think about it, the same is true of a record and a record player, of a CD and a CD player. It encodes information according to a very specific coding system, but you need to know something about the reproduction process in order for it to work. And what I'm going to argue is that one possible trajectory through the evolution of software is that whereas initially most computers really conflated these three things, over time these aspects were teased farther and farther apart. And that has had some unbelievably good effects, and it's also had some more subtle effects that we maybe have to watch out for. Okay, so that's my staging. Good so far? Wave hands if good so far. It is really fun to watch people do that. Thank you for indulging me. Okay, so let's assume that we're going to go with this simplistic definition that software is how you tell the device what to do, one way or another. So it's a self-contained representation of some kind that when you have a machine on which those instructions are designed to be followed, the machine will do some hopefully useful task as a result. When Ed Lazowska asked if I would do this class, he asked me to talk about the ENIAC computer and the origins of software. And it turns out that those are pretty separable in a lot of ways. But since we're picking that as a reference point, and if you don't know what ENIAC is, don't worry, you'll find out shortly. As a rough dividing line, we can say that for the most part, devices built up until ENIAC, and perhaps including it, were pretty special purpose devices. So a loom, for example, I mean, you can tell it to weave a number of different kinds of patterns, but you cannot tell it, for example, to bake a cake. Right? So they're special purpose devices, but there was some way to tune what the functionality they did have. And in general, in those devices, the software, such as it was, really is closely tied to the physical organization of the device. So the Jacquard loom is an example of that. A census machine, which was built by Herman Hollerith. That's actually what this photo is. This is the company, or the machine that launched the company IBM in some respect. But it was the same idea, right? There was basically a pool of mercury and metal contacts that would drop down, come into contact with a card that had been punched with census data, and wherever there was a hole in the card, the metal contact would make contact with a pool of mercury and would close the circuit. So again, the cards would be useless unless you knew a lot about the geometry and the physics of the machine on which they were intended to be used. Around the time of ENIAC, what began to happen is that there was an idea that, this isn't really just a collection of circuits and electrical elements, but we can think of those electrical elements as being organized into these abstract units. So instead of thinking as, this is a bank of 10 relays, we can think of it as this is a register or a holding place for a 10-digit number. And increasingly, what you see is people start talking about the functions of the machine and the way that you set it up or program it, not in terms of the physical geometry anymore, but in terms of the logical organization. So around ENIAC is when that concept really began to predominate. And post-ENIAC, we just started getting farther and farther away from that. So that the physical configuration of the machine started to become less and less visible to the programmer. Assembly language is probably the first real example of that, although if you've programmed an assembly language, you know that for the most part, assembly language instructions are still pretty close to the machine hardware. And then when we get up to what I'll call fully modern software, pretty much it's independent of the hardware. The software expresses tasks in a language that have nothing to do with how the hardware is designed, and there's all these layers in between that actually map you down to what the hardware can do. And how those layers came about, both in terms of practical invention and the theoretical underpinnings that let it happen, is where we're going to go in the next, hour or so. By the way, who has programmed an assembly language? Wave hands violently. Wow, huge number of people. Okay, good. That'll make this that much easier. For those of you who haven't, don't worry about it. So most discussions of the history of software, somewhere along the line, have to mention Charles Babbage and his protege, Ada Lovelace. Charles Babbage was a fairly eccentric engineer who lived during the early to mid 19th century. And one of the inventions for which he's remembered, which is kind of ironic because neither of them was actually built, were the difference engine and the analytical engine. The difference engine is the sort of the better known of the two, and what it came out of is a government request that they needed to compute accurate tables in order to solve the polynomial equations that arose when you're doing ballistics targeting. And by the way, if you know, another trajectory you can follow through the origins of software and computing in general is who funded the innovations. There's a surprising number of innovations that were funded by the desire by one government to blow up the people that lived under another government. So this is one of many examples of that. And Charles Babbage came up with a machine that would implement something called the method of differences, which I don't have time to describe, but if you look it up on Wikipedia, there's a really easy explanation to follow. The basic idea is if you compute the first few terms of a polynomial equation by hand, you can compute all the rest of them automatically through a procedure that just requires adding and subtracting. No multiplies or divides. And that's pretty important because for the past almost 200 years up to Babbage's producing the difference engine, there actually was a lot of history of people building mechanical computing devices that could add and subtract. So the idea that you could add numbers mechanically was pretty well established. And his contribution was, here's a way to apply this idea in a more general manner to solve a useful scientific problem. And it was essentially a fixed purpose calculator in that regard. You could compute anything you wanted as long as it was a polynomial. And during the design and construction of that, which by the way, it was never finished, if we're going to talk about interesting firsts in the history of software, this was the first government grant for a computer project, and it was closely followed by the first budget overrun on a government grant, and the first unfinished project resulting from a government grant, not the last. While he was designing it, he came up with a much more ambitious idea for essentially making it a lot more flexible than a fixed-purpose calculator, and this idea he called the analytical engine. So the idea is that the processing mill, which is what he called the part of the machine where the additions and subtractions are actually done, rather than presetting it in a specific way to, let's say, solve a specific polynomial, instead you would feed it punched cards, right? So these punched cards have a long and distinguished history, and each punched card would have a pattern of holes that, using a system of rods and levers that were built into the machine, would set up the gears of the machine to do a particular kind of operation. For example, an addition as opposed to a subtraction. There would also be variable cards, so that instead of setting the machine dials manually for the numbers that you wanted to add or subtract, again, the numbers would come in on these punch cards, and rods that would drop through the holes would cause the machine's knobs to be set up. He called them instruction cards and variable cards. And by the way, those names persisted up until Fortran, roughly. So about 110 years after he came up with the terminology. He also said that there would be this thing called a store, which was basically a place where a temporary result that had been computed in the mill could be moved off for later storage, and that's what we now think of as memory. And in order to have as flexible as possible a way of doing computations on this thing, he postulated that the deck of cards containing the instructions would have the equivalent of jumps. So, you could have a card that said, okay, at this point the operator needs to take these cards out of the deck, reorder them, and start the machine again, right? That's a jump instruction. It's a jump backwards if you reorder the cards. It's a jump forwards if you just take a chunk of cards out. He had the concept of a subroutine, right? When you have to compute a common subresult, like taking a square root, you go to the cabinet where there's decks of cards to do common things. You grab the square root deck, load it into the machine, let it run for a while, and when the deck has been processed, you take it out and put the original deck back in, pick up where you left off. So all of these concepts that are the elements of modern programming really were present in his description of the analytical engine. And unfortunately, the machine milling technology of the time was just not up to the magnitude of what he wanted to do. This is one of my slide typos that never got fixed. It was never built until 1910, when his son posthumously built a small chunk of it essentially as a proof of concept. But a real working analytical engine was never built. The important contribution is that it was a leap from kind of calculators that were fixed-purpose devices operated by a human to calculators whose operation could be sequenced automatically using what was effectively a program, right? A deck of cards, each of which had a punch code on it saying what to do.
Question for Microsoft?
Yes, sir.
So he was British, and the British were at war with France for a good part of the early 19th century. So how is it that the French government was it? Oh, I'm sorry. It says first government. I thought it said French government. France. I was
you mean
asked.
this word?
Never mind. Yes.
Yes.
Sorry. My bad.
But if you want to go off on an interesting tangent offline, not too much earlier than this, the French government was developing one of the first long-distance communication systems capable of transmitting arbitrary alphabetic messages. Go look up Napoleon's optical telegraph for a lot of fun. Okay, so may I continue then? Great. So you can't mention Charles Babbage really without also mentioning his protege, Ada, Countess of Lovelace. And she's, well, not the only Lovelace that history records, but she's the one that's remembered in this particular thread of history. She was widely acknowledged to be one of the most brilliant women of Victorian England, and Victorian England probably wasn't the best place in the world to be if you were a really brilliant woman, especially in mathematics. It wasn't a time when women published a lot of mathematical papers, but she was very gutsy, and because she had kind of noble status, because she was the legitimate daughter of Lord Byron. After his divorce, her mom would basically not let her see her estranged dad anymore, and instead would take her out to all these society functions. And Charles Babbage, being a fairly well-off inventor, at least at the time, would hold these salons at his house where he'd invite influential, smart people over to talk about things. This is where the two of them met, and where she learned about the difference engine and later the analytical engine. She became his longtime protege, and she's considered one of the few people who really understood the potential of the analytical engine, not just as a calculating device, but also as a device for symbol processing. So she sort of has the unofficial title of the world's first programmer, because once she had read and understood Babbage's description of what the analytical engine was supposed to be, she actually came up with a procedure, and I mean a procedure expressed in terms of analytical engine instructions, for computing Bernoulli numbers. Now, if you don't know what Bernoulli numbers are, do what I did. Go to Wikipedia, and just even understanding what they are, if you're not a mathematician, is fairly subtle. But it's very likely that the thing she came up with is probably the world's first computer program, because it was the first expression of how to compute a particular result that was written expressly for a machine that had a limited instruction set. In other words, this is not one human being describing to another how to do something. It's a human being encoding in a very limited, with a very limited set of expressions, how to automatically compute that result on an artifact. Perhaps the more revealing thing is that she understood, probably even before Babbage himself understood, that just because the machine was designed to do equations didn't mean that it couldn't process other kinds of information. In particular, she understood that if you could represent other types of information in numerical form, then you could cast operations on the operations on the numbers as operations on the non-numerical things, right? So I think in lay terms, what that means is symbolic processing in the artificial intelligence sense, graphics, playback of music, anything having to do with text processing. These are all examples of automatically manipulating information that isn't numerical by its nature, but that can be numerically represented, and in which the operations on it can also be numerically represented. So she had an insight that was far ahead of her time that you could actually do this. And she wrote a fair amount about it in her journals, and again, the technology of the time, because it wasn't really enough to produce an analytical engine prototype, these ideas wouldn't really get tested until probably almost 100 years later on. She was rewarded by having a language named for her in 1979, a language that isn't particularly well regarded. It's called Ada, and a lot of people who have programmed in it don't have wonderful things to say about it. So I guess that's one possible fate that you have if you're way ahead of your time, is that you have a bad language named after you. Those are the breaks.
Armando?
Yes.
At the University of Washington, Ada was the best regarded language for I don't know how long.
Who's speaking? Somebody at UW? I can't say.
At Microsoft?
Oh.
At the UW, Ada was the language they taught all of their intro classes in for many years.
But that's different from saying it was well regarded. Was it?
Oh, but they loved it.
Anyway.
The military also uses it.
Yeah, Ada, it was essentially a DoD-endorsed language, and the idea was that it had all these constructs that would make it more, they would robustify the writing of the kind of mission-critical code that DoD applications presumably warranted. I don't know how widely used it is in that form anymore, but I'm probably being a little bit flip by calling it ill-regarded, but anyway.
Question?
Yes.
You said that this was the first time, this is at UCSD, wave at you, that someone wrote something in a restricted instruction set, and that kind of made it explicitly for a computer. How did people write or describe algorithms before this? Because, I mean, certainly there were algorithms for doing things. Was that in some sort of language, but it wasn't really meant for a computer?
Basically, people described it in human readable terms because there was no concept that the entity who would execute the algorithm would be anything other than another human being. It's the difference between reading a description of something in the CLR algorithms book versus trying to code a description knowing what instruction set you actually have. So as far as anyone records, Ada Lovelace was the first person to not only think of the algorithm, and probably there were algorithms around to do this. I don't think she's credited with inventing the first algorithm for computing this, but for being able to express it targeted to a particular machine that had well-defined limited capabilities. I think that's kind of what gives her the honorary title of first program writer. Okay, so this is probably a good time to talk about the legacy of the calculator because it's a legacy that really colored a lot of the computing developments up until about the early 1950s. As I said, by the time Babbage got around to designing his difference engine, there had already been a lot of work done on mechanical calculating devices. And I think as early as the mid-1600s, another famous mathematician who had an ill-regarded language named for him constructed the first true mechanical calculator that could add, subtract, and do a variety of wonderful other things. The military, by and large, has been the driving force for most of these innovations. And it's, at least from the 19th century onward, the main motivation was solving these difficult ballistics equations that required evaluating polynomials and taking roots of numbers and so forth. And at the time in the U.S. that we're about to jump forward to ENIAC, at about the time that ENIAC was being constructed, the machines that were in most vogue in U.S. research institutions were actually analog computers. They were machines that took advantage of physical properties of electromechanical elements to compute things in an analog manner. And the main drawback they had was that they required the parts to be machined and the parts to interact to such a fine tolerance that they were rapidly outstripping the demand, or the demand for computation was outstripping what could be practically built. But the idea is that, going into World War II, the idea of the digital computer was not at all an obvious idea. That digital representations of numbers and digital computation was going to be the way to solve math problems was really not the trend. And as far as anyone knew, software was just a plan for doing a complex calculation, right? Kind of in the style of the analytical engine. So, with that backdrop, this is where I have two slides that are out of order. Let's talk about. So it's always fun to talk about killer stats for these old computers because then we can kind of be impressed and proud of ourselves at how far we've come. So let's get the killer stats out of the way, and then we'll talk about what ENIAC actually accomplished from an engineering perspective. It was built over a period of about 8 years, which is about 6 years longer than the builders thought it was going to take. It ran for about 10 years after it was fully operational. It was 42 panels, each 9 feet tall. The whole thing weighed about 200 tons, and it was kept in one of the few rooms at the University of Pennsylvania where there was forced air cooling. A huge number of vacuum tubes and relays, and the mean time to failure of the vacuum tube was on the order of tens of hours. So you can imagine how much fun it was to run a computation many times. 3,000 manual input switches, and I do have a couple of slides coming up showing how those input switches are supposed to be used to actually solve problems with this thing. But the upshot is that the way you would program this machine is you would set 3,000 input switches to the right settings, and you would connect a comparable number of patch cables physically between these 42 panels, and it could take days to set up the problem, assuming that you got it right. Now, once the problem was set up, it could actually go very fast. In what we would call a clock cycle, ENIAC could do it ran at about a 5 kilohertz clock, although it wasn't a true synchronous clock. But the addition cycle took about 200 microseconds. And that made it kind of 2 to 3 orders of magnitude faster than the differential analyzer for the precision that it was able to handle. So problem setup was really, really awful. But the way that this thing is intended to be used is, here's a set of ballistic equations for a new type of weapon. We have to configure the machine so that it solves the equations correctly for that weapon type. But once it's configured, we're actually generating just large tables of constants, right? That's the kind of computation it did. So the usage model was that you're going to amortize the setup over a huge number of computations anyway, Therefore, it's not a big deal, right? And by the way, they didn't use the term programming for ENIAC. They called it setup. You would set up the machine to do a computation, and then you would do many, many, many instances of the computation. So how, what were these 42 panels actually about? What was it used for? And now I have to, there. So if you're an acronym freak, electronic numerical integrator and calculator, you'll notice the word computer does not appear. It is a calculator. And in fact, it's a direct descendant of the automated calculator legacy in many ways. In fact, it's really only a zeroth order simplification to say that it was a re-implementation using vacuum tubes of a sequenceable calculator ideal, very similar to what Babbage had proposed. In fact, in some ways, probably less flexible than what the analytical engine would have been had it ever been built. Physically, the ENIAC had a bunch of different functional units. So it had 20 accumulators, and we'll talk in a minute about why they were called that. But if you ever programmed an assembly language and wondered why the hell it's called an accumulator, you're about to find out. The accumulators could add and subtract, but that's all. There were specialized functional units for doing multiply, divide, and square root. Each accumulator would hold a 10-digit number in tens complement. So this was a digital computer, but it was not a binary digital computer. The thinking was, we already do everything in base 10. Why should the computer be any different? And the idea of reliability and efficiency and other reasons that you might go binary hadn't really entered the picture yet. But if you do the math, a 10-digit tens complement number takes about 4 1/4 bytes. So ENIAC had on the order of 100 bytes of temporary storage total. There was a unit called the constant transmitter, where you could put in a stack of punch cards, or it also had some dials you could set, and it would transmit the various constants used in your computation at the appropriate times. And there was a thing called the cycling unit, which was sort of like a clock, but not exactly. And as we'll see in a minute, in terms of programmability, it was probably less flexible than the analytical engine and somewhat more flexible than the difference engine. So what would it be like? What was ENIAC software like? They didn't call it that, right? And they didn't call it programming. But there was a concept of setting up the machine for a calculation. And this is my brilliant use of PowerPoint art to try to illustrate conceptually what your life would have been like if you were an ENIAC setter-upper. So here's the scenario. Consider that you have 3 trained monkeys, and each one of them has a dime store variety calculator, except the 2 of the monkeys can only add and subtract. The 3rd monkey has a calculator that can multiply, divide, square root, and do other exotic stuff. And at each time step in a computation, each monkey looks at a colored lamp, and the colored lamp tells him what to do. He can either show his calculator screen to another monkey, who will then add that number to the number shown to him, right? So those are the first 2 actions. Or he can replace his number with a number that's written on a blackboard, which all of the monkeys can see, right? So basically, depending on what color the lamp is, I'm going to do one of those 3 operations, right? Show my result to someone else, add someone else's result that is shown to me into my own result, or just replace what I have by punching in a new number. That's it. Those are the 3 things. And your goal is, given those constraints, you need to compute the one solution to the quadratic equation. Right? It's arguably one of the most trivial equations you can imagine programming. And your deliverable is a step-by-step list where at each step, you're going to tell me what lamp is lit for each monkey and what has to go on the blackboard. Yes, I heard a snort and a chuckle, or maybe something that was in between the 2.
Question from Microsoft?
Yes.
So I assume once you get one of these things set up, you really want a lot of data to flow through before you have to change all the patching and all of that.
Right. And as I said before, the usage model for this is you set it up and it takes forever. But once you have it set up, you're basically generating a lot of tables. You're basically running the same function with a great many different arguments. So once you have the logic set up, you can kind of crank out results pretty fast. But you can imagine, if this is your view of the world, right? Part of the setup problem is just converting this equation into a list of what the physical steps are, let alone converting the physical steps into k-blanks. So you have problems like, in what order do you compute the results? Where do you keep the intermediate results if each monkey only has one calculator and there's no external store that you can swap out to, right? You have to choreograph things to make use of this very limited storage space. And by the way, they're roughly synchronous. So whenever one monkey changes what they're doing, they're all going to change what they're doing. So you have to, if that means that one monkey should really do nothing, you have to basically tell them the equivalent of look at your own number and copy that in so that they don't lose the result, right? It's, as I say on a future slide, it's VLIW from hell. So for those of you who know VLIW, you can have a chuckle at my expense. This diagram comes from a paper that was written just a few years ago by some other computer history buffs that tries to get at what was the architecture of ENIAC. And it's kind of a tricky question because ENIAC didn't have an architecture in the way that we now think about computer architecture. This is the closest that they could come. You notice that they have something that's called a data bus and a control bus, but in fact, again, those of you who are not geeks, don't worry about this. Those of you who are geeks, these aren't buses in the traditional sense of everything can talk to everything else. These are trays, and you can connect any two units together by laying a cable in that tray and plugging the ends of the cable into the two correct things. So, the good side is that these accumulators, each accumulator can add and subtract, and there's 20 of them. So you really can do 20 parallel adds. That's pretty good, especially for the time. But the scheduling of a problem to actually take advantage of that was gnarly. Here's a simple example from the same paper, and here I'm going to show you how you would have wired the machine. You're going to compute these three quantities in parallel. The blue and the red lines represent physical cables that someone has plugged in to the various units. And here's a computation that completes in 3 time steps, right? In the first time step, what happens? There's an arrow. So this A1 cable sends an initiating pulse to all 3 of these accumulator units. And on time step 1, the subtract output of accumulator 5 is going to get forwarded to the alpha, or the first input of accumulator 4. And what do accumulators do? They add whatever is coming in on their inputs to whatever they're currently holding, right? That's why it's called an accumulator. It accumulates the result by addition. If you want to subtract, you just send the tens complement of the number instead. And how do we know that it's going to come in on the alpha input? Well, because those are the two that are connected together, and somebody set a dial on this unit saying on the first time step, you're going to read your input from that connector. So that means that now A4 has whatever it was holding before minus the contents of that accumulator. This is a nifty erase feature. And during the same time step, we're going to do this, right? We have a wire going from the add output of accumulator 5 to the alpha input of accumulator 6. And if accumulator 6 initially contained value C, now it contains this, right? So that's time step 1. What happens during time step 2? Well, surprise, for the second time, that same operation, accumulator 5 is going to forward to accumulator 6. Why does that magically happen twice in a row? Because there's another secret parameter, which is the repetition count. The repetition count says on a given cycle, do this operation more than one time, right? So this is yet one more variable that you can take into account when you're trying to schedule your calculation. And then on that same time step, the constant transmitter, which has been preloaded with 359, is going to feed that constant value to the beta inputs of 2 other accumulators. So they're going to both add 359 to whatever they had before, and the end step is that that's what the 3 of them contain. And I have no idea why you'd want to compute this, but it gives you an idea of the kind of planning you have to do to set this monster up. Okay, so this is over.
From San Diego.
Who are not geeks can tune back in. Given how much of a pain in the butt it was, what is noteworthy or significant? Like, why do we care about ENIAC? Why do people think that it's an important aspect of the delivery of the development of software?
Armando, I think we've got a question from San Diego.
Okay, which was San Diego?
Yeah, I had...
Upper right? Okay.
Yeah, while we were still looking at the setup of the ENIAC, I was just going to mention or observe that if what it's intended to do is calculate like ballistics tables, it would make a lot of sense to have a bunch of independent accumulators. So imagining you might want to store position and velocity in 3 dimensions, that could take 6 accumulators that would all be able to operate more or less in parallel. But just a thought.
Yeah, no, that's a very good point, actually. And although, I haven't read sort of the detailed description of how the design was originally realized, I think it's a perfectly reasonable assumption that knowing what the target application was, they designed backwards from that. And in fact, I know that originally the number of accumulators was going to be something much less, and it turned out that people came up with sample problems, and it turned out that they needed to expand it to 20, or they'd never be able to do anything useful. So, but it's a good observation that, again, the machine was very tied to its end purpose, which was pretty specialized, and in turn, the setup or the programming of the machine was tied to the physical layout as well. Thank you for bringing that up. Okay, so what is noteworthy about ENIAC? Besides the fact that it was truly parallel, which was novel at that time, and besides the fact that now we all know where the word accumulator comes from, it's not too hard to see the leap from something like ENIAC, where you're physically plugging units together, to a true data bus architecture where all of the units are connected to a common substrate, and the instructions tell you at any given time which result should be transferred from which unit to which other unit, which is essentially how the internal architecture of simple CPU cores works more or less that way. And in fact, just a few years after ENIAC was commissioned, MIT's Whirlwind computer, which we'll come back to in a couple of slides, as well as the Mark I automatic calculator developed at Harvard, would both make this improvement. In other words, they would rely on punch cards with instructions to actually indicate which unit should forward results to which other unit and what operations to do next. So that was sort of a critical step in separating the hard physical layout of cable plugging to something that was more controllable from punch cards. Right? And at that point, we're kind of back to the level of sophistication of the analytical engine. In fact, you could probably think of the Mark I as an analytical engine realized with electromechanical relays instead of gears. But we'll come back to that. Okay. The real ramification of this idea of being able to represent programs as punched cards is an insight that I think Ada Lovelace may have dimly had, but that didn't really become an important driver until Alan Turing, who we'll talk about next. But the deep insight is that if you can represent, if you can divorce the instructions for doing something from the physical hardware. In other words, instead of talking about cables and plugs, you talk about cards with holes. And then instead of cards with holes, you talk about numerical patterns that match where the holes would be, right? It seems like a small step. But once you get to that point, programs are data, just like the data that your equations operate on. And, if you're going to talk about a sequence of ones and zeros to activate the machine elements, those are just binary representations of numbers. And that means that for what it's worth, one can imagine operating on the program as if the program were data, right? And that, in some senses, is part of the essence of the stored program computer idea, which von Neumann unfairly gets credit for, even though he didn't make it up. So the non-obvious implication of being able to separate even a little bit the expression of what is to be done from the machinery for doing it is that all of a sudden the program itself can be operated on like data. And this is, at the time, was highly non-obvious, even though it turns out today there's technology we use all the time that takes it for granted. As usual, it took someone really smart to pick up on this idea and run with it. And Alan Turing, his name survives him in the form of things like the Turing test and Turing completeness and Turing hard, came up with a formal model that tried to sort of capture the essence of what computation meant, in the sense that you're building these machines that can do a limited repertoire of things, they can operate on data. Is there some formal construct, like something that you would find in the realm of mathematics, that expresses the abstract essence of what's going on here and that is really, truly independent from any particular hardware instantiation? So the easy-to-understand version of a Turing machine is what is called a finite state machine in electrical engineering. And you can think of it as an abstract device whose next behavior depends only on what behavior it just did, and if it has any sensors bringing in data from the outside world, what those sensors are telling it. And it's much easier to show than it is to describe formally. So here's my simple example of a candy machine where candy costs $0.25. So it's kind of an outdated example. The idea is that abstractly, we think of this as starting out in this S state, and I'm assuming that people can see color on these slides. You can see that there's some of the arrows connecting the graph nodes are red, like this one, and some of them are blue, like that one.
And like many computer programs, I think this one has a bug.
It probably does. Like many computer programs, this one was written at 3 a.m. the night before it was due. Touche. And the intended functioning of the computer program, although it may very well have a bug.
I think the reject coin line is supposed to be blue.
Yes, you're right. The reject coin line is supposed to be blue. Here. This is the magic of... I like this technology
Stored
already.
program computers.
Yes, you're right. The reject coin line is supposed to be blue. So, for those of you who haven't seen finite state machines before, the idea is you start out notionally in this S state, which I've already circled, and whenever a dime is inserted, you'll follow the blue arrow out of your state, and if a nickel is inserted, you'll follow the red arrow. And I haven't put in the arrows for pennies, but bear with me. So the idea is that if you insert a nickel, and then another nickel, and then another nickel, and another, that gets you to 25 cents, and candy is dispensed, and you're happy. Or you could you could get a nickel followed by a dime followed by a dime. That would also work, right? So this is kind of a trivial example But I think it captures the concept of the finite state machine. The formalism for expressing it is a little bit more subtle to understand, and it's expressed usually in terms of an infinitely long paper tape. The paper tape has little cells on it, and each cell can hold a symbol. And the symbols come from a limited size alphabet, so it can be just 0 and 1. It can be any finite number. And in addition to the tape, you've got this table of instructions. And the table really just captures what this diagram is trying to tell you. In other words, for every possible state and every possible combination of inputs that you could see while in that state, it tells you what state to go to next and whether to change, basically whether to change what's written on the tape under you. In this example, that corresponds to something like dispense candy, right? Writing the tape means I'm going to make a change to the world, which is a candy bar gets spit out in response to something happening. So the machine definition is finite, right? The table is finitely large because the number of possible states is finite by definition. The storage is infinitely large, but that turns out to be theoretically, it's not a problem for implementation, even though we can't make infinite memory machines, at least not this year. And this is sort of a formalism that captured the essence of computing. Now, why would you care about this formalism? Well, once you have a formalism for something, you can prove things about it. And as it turns out, there's an entire field called computability theory that really came out of Turing's work and his ability to distill the essence. And remember, this is independent of any physical implementation, right? This diagram doesn't say anything about how you would physically build a machine that does this, but it does tell you what is the essence of how that machine would be controlled if you were to build it. The idea that programs are data and can be manipulated formally and that you can prove things about them has led to a number of important results. But the one that we're going to focus on for this slide is universality. And a simplified statement of that result is as follows. If you give me a description of a particular Turing machine, right, and remember, if I back up, my description is really just a table that captures this transition diagram. So you find a way to encode that onto one of these infinitely long paper tapes, so at least you know space is not a problem. You hand me that, and I can prove that it's possible to make a machine that will read that tape and behave the way your original machine would have worked. Right? The properties that allow it to do that make it a universal Turing machine. So it is a specific kind of machine that can be made to imitate the behavior of any other Turing machine. This is a really, really deep concept. And it has huge practical importance, which we today take for granted. The practical importance comes from the fact that it means that if you build a physical computer that can be shown to have the properties of a universal Turing machine, then in principle, that computer is just as powerful as any other computer you could ever possibly describe with the Turing formalism. If you think of a compiler or an interpreter, that's really where this concept comes from, right? And again, those of you who are not geeks, you can tune out for a second. But an interpreter is really just a way of saying, you're going to give me a list of instructions that is written for a machine that doesn't really exist. I'm going to translate that into a set of operations on this piece of hardware which does exist. And the result is going to be that the piece of hardware is going to behave just like the imaginary machine for which you wrote the instructions. That is an amazingly deep concept that we take for granted now. And those of you who, like me, had to live through the transition of the Apple Macintosh from when it was 68,000 to when it was PowerPC.
120.
Sorry?
120. It was 68,000 processors.
Yes. So the original Mac series was all 68,000 processors. Apple radically moved the entire Mac line to the PowerPC architecture in the late 90s. And in order to make sure that people could still run their old programs, they provided an emulator that would take 68,000 code and run it on the PowerPC. Right? This is the Turing machine concept exactly at work. So huge practical importance, and launched a new field of computability theory.
Question from San Diego.
Yes.
Since a program can be treated like data, a program could also operate on itself. Are you going to talk anything about self-modifying programs?
Not
why they're not used?
But I am going to talk toward the end about viruses, and that may be at least tangent to the question that I think you're asking. But yeah, you're right. One of the implications of a program being data is that a program can operate on itself and make changes to itself while it's running. But given the number of hours I've been awake, that makes my brain hurt right now. So you'll forgive me if I skip over it for now. Good question, though. Okay.
Can I ask something from UW?
Yes. I'm sorry. It's just hard for me to see where the hands are. Which one is UW? Okay, the lower left corner. Got it.
So at one point, just the ability of programs to be able to branch and do if-then statement was in fact considered, such programs were in fact considered to be self-modifying. Because before this point, they would just go through this sequence of steps without any branches or if-then else.
Okay, so what I think you're asking is, at what point did the idea of conditional execution become sort of part of the programming vocabulary? Is that about right?
I was just merely trying to make an observation that when you're self-modifying programs, at one point this meant something else. When people started doing if-then-else branching and jump instructions, they thought they had self-modifying programs.
Fair enough. Okay. So now we're starting to take steps away from the physical machine and towards a more abstract representation with the knowledge that we can map the one to the other. And once that observation had been made, it sort of paved the way for a bunch of innovations that, again, if technology had allowed the analytical engine to be built, perhaps they would have been realized physically a lot earlier. But one of them is the idea of the subroutine finally came back. So Grace Murray Hopper, who is probably if there are two of the best-known women in computing, they are Grace Murray Hopper and Ada Lovelace. She was a Navy officer and eventually became Rear Admiral who had been assigned to work in the computation lab at Harvard with Howard Aiken because the U.S. military, guess what, had commissioned the building of more computers designed to solve primarily ballistics equations. But it was a big improvement over ENIAC in that the way that you program these machines is you would punch a row of holes in paper tape, and the holes would essentially represent what today we'd think of as a machine instruction. The constants would be on the tape. And note that it wasn't really a stored program computer in the sense that we think of today, because the act of creating the program and creating the tape was separate from the act of executing the program, right? There was a whole set of equipment where you would punch the tape, and then there was a different set of equipment where you'd take the tape over and actually run it and cause something to happen. So it's fair to call the Mark I an automatic computer, but not really a true stored program computer, because the program and the data on which it operated were not held in the same medium and interchangeable in the sort of Turing sense. So Hopper's insight when she was working on this is that there were a lot of times when she would have to incorporate a common sub-operation, like, let's say, taking a square root, into some new program that she was trying to put together. And she already had paper tapes from old programs where if she just kind of cut out the right little chunk of tape, she would have the routine for taking the square root, but parts of it would be wrong because, in the old algorithm, you were taking the square root of 75, and in this one, you're taking the square root of some other constant. Plus, the Mark I had a number of different registers where it could hold temporary results. Maybe in your old program, the result of the square root was being stored in register A, but in this new program, for whatever reason, it's got to be stored someplace else. So she had this idea that if only you could snip out those parts of the tape and make a few changes to sort of tune them to your new problem instance, you could compile all these pieces of paper tape together, and bam, you'd save a lot of time in putting together a complete program. And that is indeed where the first use of the term compiler is believed to have come from compiling all these snippets of paper together into a long continuous tape. And what it really amounts to is the modern rebirth of the subroutine concept. And remember that I mentioned that Babbage's analytical engine had a primitive but truly a subroutine method where when the machine got to a certain point in the calculation, it would ring a bell, and the operator was supposed to go over to a cabinet and fetch the right deck of cards to perform some common subtask, right? Now it's a little bit cumbersome to operate, but that's a subroutine because you use it over and over in different points in the calculation. This instantiation of subroutines in the context of the Mark I was really the modern reappearance of that concept. And ironically, although the first so-called compiler for UNIVAC, which was really more like what we think of as an assembler, would have this capability, it would be absent from the first high-level language that was successful, which was Fortran. The next closest thing to what we think of now as a compiler and an interpreter came from the MIT Whirlwind computer. The Whirlwind was another electronic automatic calculator, and same idea that there would be a card punch where the holes punched in the card would direct the step-by-step operation of the machines, the monkeys with calculators, if you will. But the big innovation was that a few years after the machine was built, two of the scientists who were regularly programming it came up with a really neat method where you could expressed in a pseudo-algebraic markup, right? Kind of the way you would type equations to a C program or something today, and they would have this separate program which they had written that would convert your calculation into the right sequence of steps. So, in terms of my 3 monkeys slide, they had come up with a program that would take the equation you wanted to compute, and they would translate that into a list of the right operations for monkeys to perform, or in this case, for the whirlwind to perform based on punch cards. And they would automatically do things like, where do you put the intermediate results? In what order do you schedule things to make sure that you don't run out of storage during the computation? So all the bad stuff that the ENIAC setup engineers had to do manually, these guys had invented a program that would do it automatically. It was probably the first assembler. And again, what this comes from is you assemble a deck of cards by, copying the subroutine cards and sticking them into the right places. Notice that the vocabulary of what you're doing is still tied to the machine hardware, because the output of the program is these punch cards with machine code on them. But the housekeeping tasks have now been delegated to a program that has to worry about them, right? So now, and this is really important, right? Because if you're a scientist, before, you had to understand the equations you were computing, and you had to understand the physical organization of the machine so that you could do the translation from my algebra equation to a sequence of low-level instructions. Now, that ability has been encapsulated into a program, so the scientist doesn't have to know about it anymore. And you can kind of see the path that we're starting down. There was a yellow battery light blinking on this. Should I do anything about that?
Fast.
Okay. You should change your battery or switch to outlet power soon to keep from losing your work.
I'm on it.
Okay. It's being taken care of locally, I'm sure. So a couple of other noteworthy things about the whirlwind experiment. First of all, we're still not really at the full stored program computer yet because, again, the source code of your program was expressed in different terms from the object code, like a different medium. The object code wasn't stored in the same memory that was actually used during the computation. So the programming step was still perceived as being separate from the computing step. Computing didn't include programming. Computing was having a set of instructions already prepared using some other technology and then executing the instructions to crunch out a result. The other noteworthy thing is that this was the first documented complaints by real programmers, in other words, the guys who knew all about the machine and who were comfortable hand-tuning their equations to compute on it, that, hey, when the compiler generates this automatic code, it's much less efficient than what I would have done by hand. This complaint was to recur repeatedly many times, and it persists to the present day. Of course, the next big step forward, thank you, came in the form of the first, arguably the first really successful high-level language. And I realized that from the perspective of today, calling Fortran a high-level language may seem questionable to some people, but given that you've just seen what programming was like up until the early 1950s, you have to imagine what kind of a revolution Fortran must have seemed like when people saw that you could express your computations like, I don't know if this is legible, by the way. It's barely legible on my screen. But if you could read it, you could see that it is a vaguely sort of English-like, sort of algebra-like representation. And if you squint hard enough, even if you've never written a line of code in your life, you could probably figure out that this computes something that has quadratic stuff in it. Right? So the idea that you could express what you wanted to do at that level and that you would kind of magically be able to have that converted to a format that the computer could execute directly, in 1957, that was huge. And Fortran was an immediate hit, in part because you didn't have to know the physical implementation of the machine in order to use it. This was probably the first industry realization that most computer users do not want to futz with languages and systems and peripherals. They want to just get their work done. It's not clear if this message is really sunk in or not, but this was the first time that they realized, wow, scientists really love this. To be fair, Fortran was not the first attempt at a high-level language, but it was probably the first that was widely successful. And one of the reasons for it had to do with the fact that the co-designer of the language, John Backus, was also a co-designer of the IBM 704, which was a kind of hybrid calculator computer that IBM had just developed, and was one of the first to have floating-point acceleration hardware. Again, for the non-geeks, what this means is that instead of just doing math operations on whole numbers, you can do math operations on decimal numbers. And as you can imagine, not just in scientific computation, but also for financial computations, that's pretty important. So in previous systems, people had designed high-level languages that would allow you to express floating-point computations up here, but when it actually came time to run it on the machine would have to essentially do a large number of integer calculation steps to mimic the whole number calculation that you wanted, the decimal calculation you wanted done. And in fact, in the days of not that long ago, before all CPUs had floating point coprocessors integrated in them, this is how life was. So part of the acceptance of Fortran was from the fact that not only did it have a compiler that automatically got you from this nice representation to the evil, ugly machine code, but that the compiler generated code that was as good as whatever anybody else could generate by hand because the hardware assist was there. And by the way, from the perspective of 1957, the compiler was just another program, right? So now we're really at the point where you have a machine code program operating on text that's been stored in memory in the same medium that the program itself is stored in. So this is the full low battery. The warning is still here. Do I care? No. I'm going to close the tab. So now we've really come full circle to the stored program concept, where not only is the program treated as abstract information, but it's operated on by another program, and the output of that is a program that actually runs on the machine, right? So now we've really closed the loop of having stored programs and really take advantage of the programs as data formalism. By the way, this is, in case you're wondering, this is the cover of the customer manual for the very first commercial Fortran system ever shipped. It's online somewhere. So the battery indicator was up here, but now it went away. So I made it go away. I assume that's okay. That's probably fine.
Question from you now?
Yes.
Why is Fortran still so popular, and what evolution did it went through? I mean, there are still people using it.
One of the reasons it's popular is because there's a lot of legacy code in it. A huge amount of Fortran code was written. And so you can imagine that in 1957 there was a pent-up demand from the scientific establishment to be able to take advantage of computing, but basically unless you were also willing to become an amateur electrical engineer, you didn't really have access to the power of the machines. And Fortran was among the first widely deployed successful languages to give you that. So there was a flood of effort. And, of course, as soon as everybody realized Fortran was a hit, that was the thing to use. And it was really quite a long time before a language came along that could really displace it. In commercial use, COBOL actually enjoyed a fair following just because it was supported by IBM equipment. And even though it was designed as a language that anybody could read and understand, pretty soon people came to figure out that 3 months after the program is written, even the programmer who wrote it doesn't understand it, let alone anybody else. But there's a huge installed legacy base for both of these. And that's my understanding is that most of the money spent on Fortran development is motivated by legacy code concerns. I may be wrong about that.
Armando,
I don't know how much new code is being written in Fortran today compared to new code being written in other languages. Yes?
Armando, could you double-check your mic connection? After the person came in to replug in the laptop, we were sort of...
Maybe need a new battery or something.
Can you hear me now?
Yeah. Yep.
Can you hear me now? The mic seems to be okay. Let me just try changing the way it's attached to my shirt.
It's good now.
It's good!
Maybe you should change your shirt.
You don't want that. Is this okay?
Yeah, that sounds much better. Keep going.
Okay, great. Thank you.
From
Yes.
UCSD?
Yes.
Or a comment, actually. I've noticed that a lot of Fortran is still heavily used in some scientific fields just because it ends up being faster or easier to express concepts, most often in nuclear engineering, actually.
Well,
which is
okay, I'm
weird
gonna say
because
something
they actually
that's
have classes to this day at top universities on writing stuff in Fortran in order to model certain things, and it comes more naturally, I guess.
Okay, so I'm going to say something that's going to get me in a lot of trouble, but that's okay because it's an opinion. There's two aspects. I think there's at least two aspects to thinking about expressing the solution to a problem in terms of a computer language. One of them has to do with I have a set of low-level operations that I have to do, and I have to get those operations expressed in whatever medium I have. And I can imagine that there's some strength to the argument that Fortran is pretty direct for that. But the other aspect is, what is the larger structure of the problem? How complex is it? Is it just kind of straight line code, or is it a problem that has a lot of bifurcation? Is it recursive? There's a lot of problem structure elements for which I would probably argue that Fortran is not the optimal choice. So it may be a case of it has a short learning curve because it's sort of so direct and so concise. but at the same time, the price you pay for the short learning curve is that it's awkward to express some things. I don't know though. It's just a hypothesis.
Kind of just raw performance point of view, until recently Fortran didn't support recursion, so you could kind of get around using a stack in some cases. And also, your arrays weren't allowed to overlap, apparently, when you passed them into subroutines. And that meant that it was a lot faster than C compilers for many, many years. I don't know how much of a difference there is today.
That's a really good observation. And if you're running jobs that take hours or days to run, then that extra few percent of performance might actually make a big difference.
Also, if you spend a year developing your matrix multiply routine, and you take 10% into the compiler, that's probably
fair enough. Okay, well, score 1 for Fortran. I'm not dissing it, by the way. I just don't use it. But I think that the upshot is you can see the pattern developing here, right? By the time Fortran was introduced, what we think of as modern languages had really begun to evolve. So if we think of ENIAC programming is still we're at the level of physically configuring the machine, and by the time of Whirlwind, we are having a program that does that configuration for us. By the time we get to Fortran, really all you're expressing is what the task is, right? Nothing about the Fortran code on the previous slide gives you any suggestion as to what the underlying machine design is that's going to execute it. So there's, once we got to this point where you could be a software person or you could be a scientist who wanted to use computers without being able to understand the design of computers, the next two big revolutions that really took off from this, one of which we're not going to have any time to talk about, which is integrated circuits that made everything affordable, and the other, which we will talk a little about, is the research models and business models that were enabled by the unbundling, in some sense, of software from hardware. So probably the next big milestone from a software engineering point of view was the IBM System 360, which I know you've heard about already at some level from Steve and others. And the term that we now call computer architecture is widely accepted to have been introduced by IBM to describe the 360 approach, which was revolutionary at the time. The idea is that in the 360, the assembly language that programmers would work in, even though it was still pretty low level, it would only reflect the logical organization of the machine. So you wouldn't talk about circuits or adders. You would talk about operations the machine could do, kind of primitives. And each different model of the 360, and there were, I think, 6 different models at the time that they introduced the line, would leave it up to its own designers on how they were going to achieve the results of those instructions in terms of microcode and circuits. So it was basically adding yet an additional layer of insulation here so that even the assembly language programmers, they had to know that all 360s are capable of the following low-level operations, but they didn't have to know just how those operations were designed into each machine. More expensive machines might have faster support for certain operations. For example, a faster machine might have a dedicated multiplier and divider, whereas the slower machine would have to emulate multiply and divide by doing adds and subtracts, but the assembly language instruction would still say multiply, and the programmer wouldn't really have to worry about which type of machine it was going to be run on. Now, of course, today we take all of this for granted, but again, when the 360 came out in, I think, 1964 or 65, the idea was not only revolutionary from a technical point of view, it was revolutionary from a business model point of view. Because for the first time, the company could make the value proposition that, hey, buy a small 360 now, upgrade it in 2 or 3 years, and all of the software that you spent time developing will still work. And in the case of the 360, it wasn't only the software. IBM came up with a standard way to, I was going to say virtualize the I/O, but that's geekly. IBM came up with a standard for how the circuits that talk to input and output devices like printers and card punches would work, and they made a corporate decision to standardize that on all 360s and on all IBM equipment, like punch card readers and printing terminals and stuff like that. So in fact, if you upgraded your 360, not only could you reuse all your old software, but your old printers would work. And conversely, if you bought a new high-speed printer, you could just plug it into your 360 system, and all of your programs would know how to talk to it. Because they never had the concept of a specific printer, they had a concept of this generic printer type. So again, these are things that today when we think of a generic printer device driver, we take this stuff for granted. This was brand new in 1965, and it was the first real step in the total decoupling of hardware and software that has really been the Intel-Microsoft strategy for about 3 decades now. The other noteworthy thing about this project is that it was the first public revelation of the hard lessons learned from a human relations and engineering management point of view of trying to do a project that was this gargantuan in scope. If you have not read The Mythical Man Month, you should read it, because all of the typical myths about how software is developed are pretty well busted in there. If there's any chance that I could get some water, that would be tremendous.
Question for Microsoft.
Yes, sir.
Were there any programs before this point that would take a program written for one model and translate it into a program that would run on another model?
None that I'm aware of, but that's a big caveat because what I don't know can fill volumes. But as far as I know, I think part of the reason for that is not that it was not technically possible to do, but the entrenched thinking was that you get the computer, you write the software for that computer, right? The idea that software was separable from a physical model of computer hadn't really taken hold yet, even though it was already inherent in the separation of the software as artifact from the computer as artifact. No one had really taken the next step of saying, well, could we take the expression of software written for one computer and convert it into the expression of software that would run on another? And as I say, someone may have done it, and I just don't know about it. I didn't find anything like that in my research, but it could be.
Well, there was one instance where Honeywell had a program called Liberator, which would translate IBM code to Honeywell's own machine.
It would do binary translation, or it would emulate the code on the Honeywell machine?
It would do translation.
Okay, well, there's a data point for you then. I wasn't aware of that, but thank you for...
I think IBM made an emulator for its earlier late 50s business machines.
But that was considerably later on.
Right? Well, I think at the last moment they managed to make it work sort of before the 370. That it was a selling point for the 360 already at the last moment they made that work.
Right. Although I think the question was, prior to the 360 interchangeability, had anybody tried to do this? And it sounds like somebody had, and I just wasn't aware of it.
Yeah, Armando, why don't you kick your microphone again? We're getting the same problem.
Is it at the front? I don't know if it's at the microphone key. I haven't done anything to it. Is that any better?
Yep.
Okay, weird. Just reboot it and it works again. So in the meantime, so at this point, IBM was enjoying sort of huge success in the field, and they perhaps weren't aware of the cultural trend that they had started by completely decoupling the software from the hardware and giving you a range of machines that could all run the same software. I mean, what a concept, right? But at the same time, an upstart little company on the outskirts of Boston, which was among the first computer startups to aggressively recruit new college grads out of a major university, was coming up with a low-cost series of machines that it branded mini computers. And the mini applied to not only the size, but the packaging and the cost. The idea was that for about $100K, you could have one of these. And this is at a time when IBM's price point was 5 to 10 times that, just to get into the game. And also, perhaps inadvertently, because it was the kind of machine that got away from the priesthood of computer operators and was a computer that was hacker-friendly. And it was entirely for business reasons that this came about, but it turned out to be profoundly important. For the geeks among you, the PDP-8 is widely believed to be the first commercial use of true DMA. IBM was doing something that gave you fast I/O, but they had dedicated separate processors and it cost a buttload of money. And it was the first use of indirect addressing and other hacks to extend the address space without having each instruction encode a large address word. Non-geeks, don't worry about it. The interesting side effect of the PDP-8, besides the fact that it was hugely successful because of its price point, is that it was really the first example of open APIs in a commercial product. All of IBM's products and most of its competitors' products were highly proprietary. The idea was that, maybe you would get some guys in your staff to write software, but probably you would contract out to IBM's software services business, which was doing very well, and they would write the software for you. And, heaven forbid if you actually wanted to modify something about the machine internals, that was just not done. DEC realized that in order to compete with IBM, they had to help their customers be a little more self-sufficient because DEC couldn't afford to field the kind of service organization that IBM had spent several years building up. So they would actually distribute for free really cheaply printed technical manuals, user manuals, programming manuals, not only to their customers, but to prospective customers. I mean, they would basically bulk mail these things, hoping to get people interested in buying a DEC machine, and essentially encouraging customers to learn about their system and play around with it. The fact that they had set out to design a small and simple system that they could sell for a fraction of what IBM was charging meant that their assembly language was pretty simple, their architecture was pretty stripped down, and a good assembly language programmer could kind of pick it up pretty fast. And in fact, if you're a fan of computer trivia, the PDP-8 or one of its near relatives was the first machine to be used to control the lighting for a Broadway show. That was a chorus line in 1975. It was actually not a PDP-8. It was an OEM model of it whose name escapes me, the EL1 or LS1 or something like that. And those of you who live in the Bay Area, those information displays, red signs that light up over BART platforms, were originally controlled by a PDP-8, although I hope to God they're not today. So there was no real engineering breakthrough in the PDP-8, but there was a massive cultural shift that resulted from the almost accidental fact that this computer turned out to be pretty hacker-friendly, both because of the much, much lower price point and because DEC was, as a matter of business strategy, encouraging people to learn about how it worked and play around with it. Because right about in the meantime, some smart guys at Bell Labs had an underutilized PDP-7 that they wanted to be able to use for text processing and playing games and other stuff like that. And in a play on Multics, which was a fairly over-designed research time-sharing system that MIT had developed and published a number of papers about, these guys came up with something called Unix, which, by the way, was originally spelled like that. And I don't remember what the provenance of the X was, but it was a direct play on Multics. The idea was that it was going to be a lot more stripped down. It was going to be easy for a programmer to understand. It was going to fit on this much more modest machine, a PDP-7. And kind of to go along with it, Brian Kernighan developed this new, very modest programming language that was compact. He called it C because it was influenced by two other languages that he had been familiar with. One was called B. The other one was called BCPL. So if he had gone on to design a third language, it's not clear if it would be called P or D. But the idea is that C would give you some of the high-level language constructs like looping and subroutines and simple data structures that were characteristic of high-level languages, but it would also allow you, when necessary, to access machine-level structures. You could address individual machine words. You could manipulate memory objects directly, and you could kind of play fast and loose with whether those memory objects were supposed to represent a number or a character or something else. And because of this dual nature of the language, over time, the Unix operating system, which was already compact and elegant by design because it had to fit onto a small machine, was mostly rewritten by 1973 in C. And again, today we take for granted the idea that you compile the OS kernel, but in 1973 it was pretty revolutionary that here's an operating system where you can not only view the source code, but compile it down to different machines. Like the idea that the same operating environment would run on different machines from different manufacturers was pretty much a new concept. And the missing pieces of that puzzle came a couple of years later when, using some support from ARPA, Berkeley basically rewrote the parts of Unix that AT&T was claiming belonged to it and could not be distributed. At that point, there was a freely available version of Unix that anyone could download, and DEC had just come out with a machine that was the anointed successor to the PDP-11 called the VAX, which was, again, a huge success because universities could afford it. So, put yourself in 1973. You can get a computer for about $100K that was, as good as anything IBM was offering at an entry level. You could get a free operating system in a language that most programmers could understand in a short amount of time. You could compile it to work on this machine, and you could give away the results. And in 1982, Sun, which had just been founded out of Stanford, decided that they were going to base a workstation business on this model. And the rest, as they say, is history. We now take for granted that you compile the operating system largely from sources. It's source portable, so there's a concept of porting an operating system from one hardware platform to another. And Linux is really just the most recent open source manifestation of this trajectory, right? So hopefully now you have a sense of what the individual steps were that got to the sea change. So here's the last slide on chunks of history, and then we'll talk about what the impact of all this has been. There was another, just as in 1957, the popularity of Fortran revealed that there was pent-up demand among scientists for computers. A little company that was not doing well in the calculator and radio transmitter business decided that they were going to essentially cannibalize their inventory and instead start selling computers for hobbyists. So this is a computer that you have to put together yourself. It has no I/O devices. You had to provide your own keyboard, your own input and output. You couldn't program it in anything except Intel 8080 assembly language. And they picked the Intel 8080 because Intel basically had a surplus of them and was willing to make a deal. And yet, despite all that, when it was offered at $400, and that's in 1975 dollars, it was sold like crazy. I mean, they were selling them as fast as they could build them. So a young, entrepreneurial-minded Harvard undergraduate, Bill Gates, and his equally entrepreneurial-minded partner, Paul Allen, saw an opportunity. If there's going to be a lot of hobbyists buying these things, they're going to want better tools for programming it, just as the scientists who had wanted better tools in the 50s had latched onto Fortran. So there was a language that had been created a few years before at Dartmouth College. It was created as a language for teaching programming. It wasn't really ever intended to be a language for use in real production systems, but it was easy to learn. And Bill Gates basically wrote an interpreter for this language that would run on the 8080 and would fit within the resources of the Altair kit. And they quickly founded a company which was, at the time, I believe, spelled with a hyphen, and solely to create a version of BASIC for the Altair that they could license. Later on, they ended up licensing Microsoft BASIC to a lot of other popular computers you may have heard of. And that was sort of the beginning of what has now become, I believe, the world's largest software company. For those of you who don't know the anecdote about MS-DOS, that was, MS-DOS was really the move that catapulted Microsoft into the dominant position that it has now in personal computing space. But IBM had decided that, if everybody wants personal computers, we'll play in that market too. We're going to make our own personal computer, but we admit that we don't really understand software in this. We're good at big software, but we're not good at little software. So we're going to go looking for a company that would be willing to provide the software that would run on these small computers, right? And remember, by now, the culture was one could imagine software being written by someone else and plopped down onto a computer. They had been unbundled for some time. And the first person they thought of was Gary Kildall, who had written a small operating system for personal computers called CP/M, which was pretty much the industry standard to the extent that there was a PC industry at that time. He was out flying his glider when the IBM people came by, so he was unable to meet with them. And at any rate, his wife, who was a lawyer, kicked them out of the house because IBM had presented a contract that was really very unfair. It was heavily biased in IBM's interest, and you'd basically be signing away your right to ever sue IBM if anything went wrong with a deal, even if it was their fault, and a lot of other bad stuff. But the short story is that Microsoft decided to bid for the contract, even though they had no operating system to offer. And once they got the contract, they went out and hunted for an operating system that they could sell. They bought something called QDOS, which stands for Quick and Dirty Operating System, and that's really what it was, for about $170,000. They made a few changes and repackaged it as MS-DOS. And Gary Kildall, who learned about this, thought that, well, hey, I'm going to go to IBM and offer them a deal. If they have the choice, they could also bundle CP/M on their machines instead of MS-DOS. But I'm going to charge them more because, hey, my product is the industry standard and it's better. And people will pay more if it's a better product. History has not borne out his position. But the direct descendant of QDOS, for better or worse, is Windows, and it now runs on, well over 90% of all the PCs out there. So, and by the way, this was repeated with Macintosh and John Scully. Apple had every opportunity to do a much more competitive license at local disadvantage to itself, and the fact that they didn't is why, the Mac is now less than 10% of that remaining space. Okay, so that's been a whirlwind tour of the sort of intellectual innovations and how we got to the point where software has become completely unbundled from hardware. The other question that I was asked to speak to is, what have the practical impacts of that been that are non-technical? The idea of unbundling of software and backward compatibility, Intel and Microsoft would probably not exist in their current form if that was not a viable business model, right? The idea that you can retain the investment value in your software when you upgrade your hardware was unheard of before the 360 and was not really practical until the PDP-8. Similarly, the fact that the aggressive marketing done for the PDP-8 to open up the APIs and let people tinker around with it, that is the spiritual ancestor of the open source movement. And today, 2/3 or more of web servers out there rely on open source software, at least to some extent. So that trend has obviously been a very powerful one. In terms of these high-level languages, for a lot of, there was a long, long litany of carping about programmers that, people are using compilers, but the compilers don't generate code that's as good as my code. Well, the compilers have gotten a lot better, and because of Moore's Law, with the hardware actually getting faster, not only do the programs run faster, but the compilers can afford to spend more time optimizing code. So, it's gotten to the point where it's really only very select portions of code that are still favored to be done in hand-tuned assembly language, but the vast majority of the code that runs these days has been output by compilers. So, whereas once the norm was you have to understand the physical machine in detail and write to it, today the majority of programmers have very little understanding of the physical machine, and in fact, the programs that do the translation do a much better job than the human beings would ever have done in all likelihood. And if you ever write macros in Excel, if you use MATLAB to do linear algebra, if you've written quick and dirty programs in Visual Basic, then you are a direct beneficiary of this trend. Software's functionality. Software's functionality is interesting because it leads to the question, if software does something useful, then in the US that means it's protectable by lawyers. And what kind of intellectual property it is has been the subject of a lot of litigation, most of it probably foolish. On the one hand, you could say source code is like a book. You can write it down. Therefore, it's copyright protectable. And it is. On the other hand, you could say, well, it directs the operation of a machine to do specific things. That's an apparatus, and that normally would be patentable. And what if I take a piece of software and modify it or improve it in some way? Is that derivative work? And if so, is it derivative work treated like copyright or treated like patent? Until a couple of years ago, the standard was if I think of a cool new algorithm and I implement it directly in hardware, ENIAC style, then I can get a patent. But if I just publish the source code, then it's a copyright. And if I claim that its look and feel is protectable, then it's even worse. And don't even ask about business methods like one-click purchasing. The idea that the concept of doing something as well as the software implementation of doing it are separately protectable has spawned an entire subfield of what I at least consider to be mostly innovation stifling litigation. And yes, I blame Apple for this too. The impact of software as an abstract representation. So Turing was really the one who ran with the idea of making software a first-class entity that can be reasoned about, and you can prove things about it, you can manipulate it as if it were any other kind of data. And that really made it meaningful to talk about computer science as a discipline that was distinct from electrical engineering or from computer engineering or even from programming. And a lot of interesting subfields have come out of that. One of them has to do with formal methods for proving things about programs. And what I see as kind of an interesting bump in that space is that, to the extent that a program is an abstract description of a computation, one might ask what you can prove about the description independently of the hardware on which it runs. The halting problem is a well-known result out of this area, which it's sufficiently well-known that you can ask a geek near you because I'm running short on time here. But what it's really led to is a lot of work in verification and protocol checking. In other words, I have a high-level expression of a program, and solely by inspecting that high-level description, I want to prove various things about its operations. For example, I want to prove that it will, or perhaps that it will not, ever take certain actions. Bug finding and protocol checking are variants of this. An interesting question about this is what's actually being verified. And the reason I bring that up, there we go. I'm going to skip ahead to this slide for a moment. The reason I bring that up is that software is not hardware, right? And when I showed the slide with the Turing machine implementation of a vending machine, it's convenient to think of that as a physical machine, but it's really not, right? It only becomes a physical machine when the software is executed on some physical piece of hardware. When the programmer designed the software, they probably had something like that abstract state machine in mind. But when it's run on the hardware, there's a whole lot of legal states that the hardware can be in that don't correspond to anything the programmer had in mind. And usually we call those states bugs in the software sense. For the most part, it's only annoying. But if you happen to work in computer security, a bug is basically a potential security hole. Because any bug that possibly could be exploited in a malicious way will at some point be exploited in a malicious way, and usually by somebody very evil. So the fact that software has been allowed to become overwhelmingly complex and divorced from the implementation that it runs on, kind of a flip side of this effect is that it's become complex enough that the correlation between what the software expresses at a high level and what happens on the machine is not nearly as obvious as perhaps it once was. Okay. And then the last chunk. So source portability, right? The idea that you can take a piece of high-level software in something like Fortran and make it run on a variety of different machines, that's essentially taken for granted today all over the place. And you couldn't really come out with a new machine architecture unless you came out with a suite of tools to compile all of the important programs for it anyway. But the more interesting ramification of this has been coming full circle to software virtual machines. So if you think, what is the Java virtual machine? What makes it different from a high-level language? A high-level language insulates you from the operational details of the hardware and focuses on the task that you want to do. A virtual machine like Java exposes a synthetic version of what normally would be a property of the physical machine. So not only do you control what your program is doing, you have some control over the environment in which it does it. And then the virtual machine itself is mapped onto another layer. So it's actually added another layer in between, whose practical impact has been that now you can write programs that have non-trivial interactions with the operating system, can express parallelism in a way that is essentially source portable. And again, if you're not a geek, don't worry about that fact. But if you are, pay tribute to the idea of source portability and the fact that if it were not for Unix and C, it's not clear when that would have come along. So a confluence of factors in the early 70s that resulted in this cultural sea change. Okay, so that's pretty much what I have to say on this. I would go out on a limb and say that the separation of hardware and software from an intellectual perspective may be the most important intellectual bifurcation in the 20th century, for better or worse. And I think it's interesting that the concepts behind that bifurcation are not limited to what we think of as digital computers. In particular, if you, instead of software, say DNA, and instead of computing machines, say biological system, I think it leads to some provocative trains of thought as to how, what the next 50 years might look like in the biological sciences, both in terms of positive and negative impacts. If you are a fan of this topic, if you live in the Bay Area, go to Mountain View, where the SGI campus is. There's a lot of artifacts there dating from, I think, certainly as early as ENIAC, probably earlier than that. I know that they have a gear from one of the original Enigma machines. It's called the Visible Storage, and there's great docents there who will take you on a tour of really cool things. They also have a great online exhibit. If you're into retro programming, there are simulators and emulators online. I wouldn't believe it, but you can actually, the ENIAC screenshots that I showed are from an actual Java applet that you can use where you can plug things together and run computations on the ENIAC. You can also find Turing machine simulators online. There's a simulator for the analytical engine. So people who have a lot of time on their hands have been so kind as to put these things online in Java form, which makes them machine portable because of the JVM source portability. If you're a fan of extinct programming languages, check out the Hello World archive. You can Google it. It has Hello World written in about 300 different programming languages, most of them no longer around. And if you're a fan of the culture that led to terms like hacker, check out the New Hackers Dictionary, which is available in book form as well as online. It's called the Jargon File if you want to Google it. And in particular, if you want to read about this insight between, thinking in terms of programming to a machine versus thinking in terms of a high-level language, there's an appendix in there called The Story of Mel, a Real Programmer. And I think that gives a very good slice-of-life moment of what the perspective of programmers was like before software started being pulled apart from the hardware. I am 3 minutes over my time, I think, and that's all I have. But thank you for your attention. It was fun to put this together, and if there's other questions, I think we have a couple of minutes before the break.
UW, San Diego, Berkeley. Must be very.
Okay, we
Thank
declare
you very
victory.
much.
You're all very welcome.